Another important thing in dealing with electricity and magnetism is what we call Faraday's law. It is the key to almost everything in E&M. It is the one that tells us on how to generate electricity, how microphones, speakers, tape decks, and so on work, amplifiers, computer disks, card readers. It has many, many applications. The basis of Faraday's law, what it tells us, a change in magnetic field creates a new electrical field. That's the basic principle. Now, how do we translate it in what we are talking about? This is the way it looks. The EMF, or the voltage induced, is given by the change in flux, in magnetic flux, over time. In equation format, we'll worry about this minus sign in a little bit, but change in magnetic flux over time is equal to the EMF. So of course, change in magnetic flux is final flux minus initial flux over final time minus the initial time. Noting that magnetic flux is given by this, like the electrical flux. If you recall, for electrical flux, it's the same equation except instead of B, we have E. When you think about flux, think of the magnetic field as something flowing, and flux is referring to flow. How much magnetic flux is flowing in this area A. The phi is the angle between the perpendicular to A and B. We'll get back into that in a little bit. Now, note here, when you think of the flux as being given by this expression, there are three things that can change it. We can change it by changing the area of the loop. We can change it by changing the magnetic field, or we can change it by changing phi, the angle between A, or the perpendicular to A and B. This is a reminder of what the flux is. In this particular case, where we have a loop that's perpendicular to B, the magnetic flux is simply B times A, the amount of field lines that are passing through that area. Now, when we have an angle phi, remember the angle, you have to get it between the normal to A and B, then my magnetic flux is BA cosine phi. Okay. One note to pay attention to, I can have a negative flux if the field lines are going in the opposite direction. For example, here, if I have the lines pointing in the opposite direction, I'll have my flux is going to be minus BA. Okay, a quick example. Compare the flux through loops A and B. So we have here one loop. We are seeing a cross section or a cut view of that loop. So the loop is perpendicular to the screen. Okay, think of the other part of it this way. It is perpendicular to the screen with its perpendicular pointing towards the right. And in this case, it's perpendicular to the screen, but its perpendicular or its normal is pointing towards the top. Now, which one is going to experience a bigger flux? Okay, now for part A, all the magnetic field lines are parallel to N. So they look like they are flowing through that area. So phi A is just BA. Now, however, for loop B, the normal is perpendicular to B, or the area of the loop is parallel to B. None of these lines are moving through that loop. So the flux is 0. So this tells us that we have a bigger flux there. Okay, before going further, Let's re-examine the question that we worked on earlier. When we have a bar that is being moved with a velocity v towards the right of the screen in a region where we have a magnetic field that's perpendicular to the screen and pointed towards us. But instead of thinking of it like we thought of it earlier, we are going to think of it in terms of area. The area in this case, we are going to think of the area that's completing the circuit here. So we have a particular flux here that's given by the magnetic field times the area of that loop. As we move the bar, we are going to have a bigger area. So we are going to have a new flux. So at time t equals 0, when my bar is here, my flux, my initial flux is B times the area that's present in that case. But the area in that case is the area of a rectangle, that's W times L, L being the length of the bar. Now, at this instant later, at time t, the bar have moved a distance Vt from this position. So the area now, the new area A2, is going to be the new width times L. But the new width is W plus Vt. That's what you see here, times L. And my flux then is BL times W plus Vt. Now, of course, both expressions, we get them using this and knowing that theta, in this case, the angle between the normal to the area and B is 0, because the normal to the area is perpendicular to the screen and B is perpendicular to the screen. So going back to Faraday's law, change in flux over time, so the flux at time t minus the flux at time t equals 0 over t minus 0. And we calculate it and we get, lo and behold, VBL, the same expression that we got before. Now, what is the direction of the EMF? B is out of the page and phi is increasing. We have earlier determined the direction of the current in this particular case. We used the right-hand rule. We said the charges are moving in this direction, positive charges are moving in that direction. The magnetic field is perpendicular to the page, out of the page. So using the right-hand rule, we see the force on the positive charges pointing in this direction. So that makes the current going in this direction, which is clockwise. Now, let's consider for a second the magnetic field due to that current. The magnetic field due to that current, using the right-hand rule, now we are going to put our thumb in the direction of the current. Okay, so I'm going to put my thumb here, and I'm going to wrap my fingers around the wire. Now, when I do that, you see that the magnetic field due to this current is actually into the page, perpendicular to the page within that area. Okay. Now, that's one interesting thing. That's going to give us another look on what's happening. We have a B out of the page, and due to the motion of the bar, we were having an increase in flux. And what you notice here, the EMF induced, that we just calculated here, is creating a magnetic field inside the loop, of course, that's going into the page. That's going in the opposite direction than the direction of the magnetic field that we started up with. That brings us to this, what we call Lenz's law. which says the induced EMF opposes any change in flux. If flux increases, the new EMF makes the new field opposite to the original field. If the flux decreases, the new EMF makes the new field in the same direction as the original field. But you have to be careful here. The EMF does not oppose the B field or flux. It does not oppose B. It does not oppose the flux. It opposes the change in flux. So the induced EMF is going to oppose the change in flux. Okay. So what this is, if you remember the equation for EMF, is minus delta phi over delta t. Lenz's law is that minus sign that tells us that the EMF is opposing the change in flux.